Now let us calculate the probability of false alarm. In general, the probability of false alarm is defined as deciding in favor of 1 when 0 is sent. Here, probability of false alarm is calculated by integrating the density function over the appropriate region. We get alpha is equal to 0 for region 0 and the probability of false alarm, which is denoted by alpha, is equal to phi of eta dash minus phi of 0 for region 2, where phi is a Gaussian function. Now let's move on to the next question. Here the given hypothesis is H0 is y is equal to n minus s and H1 is given as y is equal to n plus s, where s greater than 0 is a fixed real number and n is a continuous random variable with density function Pn of n is equal to 1 divided by pi into 1 plus n square, where n belongs to R. Our aim here is to find out Bayes rule, minimum Bayes risk, minimax rule, minimax risk, Neyman-Pearson rule corresponding to the detection probability for false alarm alpha belongs to 0, 1. Now let us move on to the solution. According to the given conditions, we have the cost functions, that is C00 is equal to C11 equal to 0 and C01 is equal to C10 is equal to 1, and the given condition in the question was equal priors. So we have pi naught is equal to 1 by 2 and pi 1 is equal to 1 by 2. We have P0 of y is equal to 1 divided by pi into 1 plus y plus s whole square for H0. P1 of y is given as 1 divided by pi into 1 plus y minus s whole square for H1. Therefore, the likelihood ratio is formulated according to Bayes rule as L of y is equal to P naught of y divided by P1 of y, which is equal to 1 plus y plus s whole square divided by 1 plus y minus s whole square, which is greater than or equal to tau, where tau is given as the ratio of the cost functions, that is pi naught C10 divided by pi 1 C01. In this case it is equal to 1. On solving, we have y greater than or equal to 0. This is the condition which is satisfied in the region gamma 1 is equal to 0 to infinity. Therefore, Bayes rule can be written as gamma of y is equal to 1 if y greater than or equal to 0 is equal to 0 if y is less than 0. Now let us calculate the minimum Bayes risk, which is calculated using the equation C bar of gamma is equal to pi naught into R naught of gamma plus pi 1 into R1 of gamma, where R naught of gamma is equal to P naught of gamma 1 and R1 of gamma is equal to P1 of gamma naught. Now how to find R naught of gamma? R naught of gamma is equal to P naught of gamma 1, which is equal to P naught of y integrated over the region gamma 1. In the process of solving for R naught of gamma, we consider y plus s is equal to z. On substituting y is equal to 0, we have z is equal to s. In the similar way, on substituting y is equal to infinity, we have z is equal to infinity. Thus, R naught of gamma is equal to integral s to infinity 1 divided by pi into 1 plus z square. On solving, we have R naught of gamma is equal to 1 by 2 minus tan inverse s divided by pi. Similarly, R1 of gamma is also equal to 1 by 2 minus tan inverse s divided by pi. On substituting R naught of gamma and R1 of gamma in the cost equation, we have C bar of gamma, that is Bayes risk, is equal to 1 by 2 minus tan inverse s divided by pi. Now let us calculate the minimax rule. Here the likelihood ratio is taken as L is equal to P1 of y divided by P naught of y, which is greater than or equal to pi naught divided by 1 minus pi naught. On substituting the corresponding values for P1 of y and P0 of y and on solving, we have the minimax rule as gamma of y is equal to 1 for pi naught less than or equal to 1 by 2 is equal to 0 for pi naught greater than 1 by 2. For minimax risk, we know the condition to be R naught of gamma is equal to R1 of gamma, that is we equate both the costs. Thus, we have minimax risk is equal to 1 by 2 minus tan inverse S divided by pi. Now, let us calculate the Neyman-Pearson rule. According to the Neyman-Pearson decision rule, we have gamma Neyman-Pearson of y is equal to 1 for 1 plus y plus s whole square divided by 1 plus y minus s whole square greater than or equal to eta is equal to 0 for 1 plus y plus s whole square divided by 1 plus y minus s whole square less than eta. On applying componendo and dividendo and solving the quadratic equation, we have y is equal to 2ks plus or minus root of s square into 4k square minus 1 minus 2. Thus, the Neyman-Pearson rule is given by gamma 1 of y is equal to 1 for y belongs to minus infinity comma 2ks minus square root of s square into 4k square minus 1 minus 2 union 2ks plus square root of s square into 4k square minus 1 minus 2 comma infinity and equal to 0 for y belongs to 2ks minus square root of s square into 4k square minus 1 minus 2 comma 2ks plus square root of s square into 4k square minus 1 minus 2. Now let us calculate the probability of false alarm. Here we consider k is equal to eta plus 1 divided by eta minus 1. Probability of false alarm is given by the equation PFA is equal to 1 minus integral s plus L to s plus u dz divided by pi into 1 plus z square, where L and u are the lower and the upper bounds of the respective regions for decision. On solving the integration and applying the limits, we have probability of false alarm, that is alpha is equal to 1 minus 1 by pi tan inverse 2 root of s square into 4k square minus 1 minus 2 divided by s square into 4k plus 2 plus 3. Now let us calculate probability of detection. In general, the probability of detection is defined as deciding in favor of 1 when 1 is sent. It is given by the equation PD is equal to integral of P1 of y dy over the region gamma 1, which is equal to 1 minus integral L minus s to u minus s dz by pi into 1 plus z square. On solving and applying the limits, we have probability of detection is equal to 1 minus 1 by pi tan inverse of 2 root of s square into 4k square minus 1 minus 2 divided by 2s square into 4k plus 2 minus 1. Hence, the problem is solved. Now, let's move on to our last problem, where the hypothesis given is h0 is y is equal to n and h1 is y is equal to n plus s, where n and s are random variables, each having PDF p of x is equal to e power minus x for x greater than or equal to 0 is equal to 0 for x less than 0. Here our aim is to find the likelihood ratio between h0 and h1 and also to find the threshold and detection probability for alpha level Neyman-Pearson technique.